Okay, let me start just to make it on time, since we have a rather challenging program today for this workshop. I would like also to thank everybody for being here. My name is George Alexandropoulos. I've been delivering, actually, we have been working in the University of Athens in various research activities of the RIS 6G project. We are also holding the dissemination management of the whole project. And let me go directly on this brief tutorial, which actually will try actually to give you an overview of what is happening in this fascinating topic of the reconfigurable intelligent surfaces and the various things that have been happening actually within this topic. I've started working on the topic at around mid-2017, is already 6 years, and there are many things happening, many projects, many papers, and many fascinating ideas by various people around the globe. So the title of this presentation is the RIS technology. We're going to see some of today's key pillars and open challenges. And of course, there is a very strong flavor of what we have done within the RIS 6G project in the things that you will see later on. So as you probably most of you know, we're actually into the 5G advanced standardization era. We're very close. We're actually under the completion of release 18 with various new features in various groups of this 3GPP standard being actually incorporated. And all of these have been driven by various fascinating new applications. You can see some things on the top of this slide, like self-driving cars, automation, smart cities, smart homes, various things happening. And of course, in order to achieve this, there have been many techniques in various layers of the networks. And if we try to zoom in what is happening within the radio access network, the layer one, the physical layer, where actually the technology that we're discussing today is very relevant, you will see even some items that seems rather close. For example, I want to bring everybody attention on this network control repeater, which in a way seems like the sequel of the relays being already from LTE advanced within the standards, and it could be actually very much relevant to the RIS technology that we will discuss today. And of course, you will see later on, you will listen actually the opinions of our industrial experts regarding this. And of course, in every release of 3GPP, when something is being finalized, there's always the discussions of the new release that kick up. Where you will see on the top, on the bottom left of this slide, the early release 19 studies, where you can actually identify this paradigm of integrated sensing and communication, where the RIS technology can play actually a huge role as an enabling technology of this overall paradigm. And it's actually many works related to the application to ISAC of RISs have been actually proposed within this project. So moving ahead, of course, there is the vision for 6G around 2030, let's say, and already we have, let's say, this extension of the triangular shape to a polygon, including new items, the integrated sensing and communication, the ubiquitous connectivity, and of course, the hyper reliable and low latency communication, keeping, of course, the typical 5G use cases, where, of course, we're wanting to extend their KPIs to go for even more demanding numbers in terms of massive connectivity, immersed communication, which is actually, let's say, the extension of the enhanced mobile broadband, and of course, the incorporation of artificial intelligence within our communication network. So let's go directly on this, on the technology that we're discussing today, the reconfigurable intelligent surfaces. By the way, there are various other terms out there, although the RIS seems to be well established already. But when people are talking about intelligent reflecting surfaces, programmable hypersurfaces, or simply metasurfaces for wireless communications, at the end of the day, we're talking about the same concept. And we're talking about structures that are comprising of metamaterials. Another term is meta-element, meta-atoms, which are actually elements that go beyond the physical properties of naturally available elements. And those metamaterials are constructed by arranging multiple tunable elements. This depends also on the technology to fabricate such an element, which is also very relevant to the operating frequency. Some examples, PIN diodes, varactor diodes, and those elements can be placed in repeating patterns at scales that can be even smaller, much smaller than the wavelength. These are small and they're easily deployed within surfaces and can be rather thin and superficial. So the precise shape of the whole surface, the whole panel, the geometry, the size and the orientation, as well as the arrangement of these elements, can enable those smart properties. That's why we're talking about intelligent surfaces. And at the end of the day, they can be capable of manipulating in peaking waves. This means various operation functionalities like block a signal, absorb it, enhance it, or even bend it in and beyond Snell's law mode, to achieve benefits that go beyond what is possible with conventional materials. That's the idea. And of course, this reconfigurability is very relevant to the fact that we can dynamically program those properties according to the objectives that we want for the wireless operation. So the response, the electromagnetic response of those elements can be controlled independently or even in groups, right, to manage to accomplish the end result. And what's the end result with, let's say, conventional way of understanding metasurfaces for wireless is to provide this signal reflection in a programmable way, meaning that to go further than the typical geometrical optics kind of reflection that is being provided from the law of physics. The good news is that we have metasurfaces already out there, not commercialized, but in large scale, of course, and this is going to be discussed later on, but in various groups around the globe, for available in a few megahertz. And lately there's a lot of research from industry, but also there are dedicated projects, especially in Europe. We are part of one of them, Terameta, which is actually trying to design metasurfaces in sub-terahertz frequencies. So the metasurfaces, they operate at the basic level of the propagation of waves, being capable of tuning the impinging electromagnetic field explicitly in the RF domain, or you will see, although you will see later considerations of today where people are trying to go even further from the conventional way of understanding metasurfaces. And what is actually necessary is to control, that we need a control unit for this dynamic control of the impulses of the impinging waves. You will see a schematic later on describing that. But let me start with, let's say, the simplest version of a metasurface that is intelligent, is this passive anomalous reflector, where we don't have the notion of reconfigurability, but we have the notion of intelligence, meaning that there is a metasurface comprised of elements which are actually being fabricated in order to provide anomalous reflection, enabling virtual loss paths. So imagine that you want to cover a specific area where is a set of users, there's a blind spot, and you can actually fabricate a metasurface. There's a company out there that's actually selling these guys, where you can, for a given angle of the impinging signal, you can actually derive a dedicated direction in order to cover a specific blind spot. The idea is that this phase configuration is actually directly printed in hardware. So the reflection is being optimized, as I said before, for a fixed incoming signal angle. You put it there, it's completely passive, and in a way, it can provide this reflection towards the direction that there was the blind spot. So we're talking about, let's say, a smart reflector here that is not reconfigurable. That's the simplest version, and this can be fully passive. There is also now the passive, which is almost passive, as you will see later on, which is the typical version of the configurable intelligent metasurface, where we're talking again about elements, but at this time, the responses of the elements are reconfigurable. This means that we can change them dynamically according to the needs of the network or the needs of the operation of the utilization. But in order to do that, we need a controller. So this RIS, this famous RIS controller, needs, of course, power to maintain the phase profile of the RIS and sweep among the different ones. And it usually serves as the interface between the RIS panel and the entity that actually uses the RIS, for example, the network. So it's critical for this controller, right, to do wisely and efficiently this interconnection. So we'll see later on that this is quite critical, and of course consumes power. We should not forget it. Of course, The amount of functionalities that this guy is capable to provide determines its cost, its power consumption, right, and its capabilities in terms of computation or even storage. It could be attached to the RIS, or it could be attached to the entity that controls the RIS. There are different versions, and these are actually quite open things. People are still discussing about that. So going further, actually a very, let's say, demanding question regarding the technology when it was initially. You can see three very well-known papers on that. Two of them have received awards, meaning that this was a question actually puzzling various researchers on the topic, is the comparison between an RIS and a relay, which at least in my humble opinion, this probably was relevant during the attempts to introduce the technology, but it's not as relevant as it used to be right now. Because operation-wise, and of course, we're going to listen to the opinion of our colleagues later on. An RIS is intended to perform like a sophisticated multi-antenna relay. Although, as you have understood most probably right now, and you will see later on, the attempt is that its implementation is much more cost and power efficient. In addition, it is expected that the network, the incorporation of the metasurface of the RIS within the network will going to be simpler compared with a conventional relay. Interestingly, metasurfaces pave the way also for new applications that go beyond the conventional relay paradigm, and you will see later on definitely some of them. Of course, one can claim that this could be some of them, or even most of them, being delivered by a relay, but a conventional relay. But at the end of the day, if you can do it much more efficient, this is definitely something that is of profit of the wireless communication era. So RISs consist of possible very large numbers of metamaterials, while conventional relays are equipped with typical antenna elements, which means that the number of antennas they can support will actually highly determine their hardware footprint and cost. And the current implementation of RISs do not provide power amplifications, although you will see what people are discussing within this direction with the reflection configuration, which is mainly applied in the RF domain. So the computation that's being provided by the metasurface and beacon signal is being done on the RF domain with no amplification. Instead, the relays can perform this amplification, and they process the received signal in baseband. Of course, if you're doing things in RF domain completely with no power amplification, means that you cannot go really far, because there's the path loss there, especially the dual path loss, due to the fact that you have a whole route that goes through one hop through the RIS, and definitely you have extra path loss that many times might need to be accomplished, actually confronted with a specific form of amplification. The current RIS implementation cannot perform any channel estimation. Instead, conventional relays rely on channel estimation for their spatial processing, and larger RISs actually enable this near-field communications. We can provide very large RISs. We're talking about chip elements. We can place them very close together. So this can enable near-field communication, which is a very hot topic. We have been working on that also within RIS 6G, which brings forth new opportunities as well as challenges for not only communications, but also localization, sensing, and of course, their integration. We're not discussing about this option with conventional relays, and it seems that this technology helped a lot to start having this discussion. But apart from this, an RIS could be also used to provide this so-called over-the-air computing, meaning that certain portion of the needed computation to transmit and receive a signal could be actually accomplished by the metasurface over the air. In this example, what we were trying to do with colleagues within RIS 6G was to actually change the shape of the channel impulse response in order to make it having a specific form that is much easier to treat intersymbol interference, rather than doing it with transmit, or specifically we do it up to now with receive signal processing. So the metasurface, the way that the signal propagates over the air, could be considered as a part of a computation mechanism offloading the transmitter or the receiver. This could be quite relevant if you consider lightweight IoT devices, for example. But of course, one could envision also the combination of RISs with relays, meaning that the antenna part of the metasurface could be actually realized by an RIS, or you could use in a synergetic way both a relay, any form of a relay, and an RIS. These are discussion. And of course, the metasurfaces, at the end of the day, this is what Emilio also introduced before, go even further. We can envision this over-the-air programmable signal propagation by actually creating networks that comprise of many metasurfaces, which of course need to be jointly optimized with the transmitter and receivers, with a dedicated controller that controls them, all of them real time in an efficient way to accomplish certain objectives of wireless operation. And this is definitely the vision of the RIS 6G. This was the vision of the RIS 6G project, where we, all of us within the project, we actually point this term of wireless environment as a service, meaning that you can program the wireless environment in the way you want, even realizing very high demanding applications with even competing KPIs. You could envision that you have a shopping mall, and you can have an area where you have boosted spectral efficiency, another area where you have boosted secrecy, spectral efficiency, another area where you want to minimize electromagnetic field exposure, and this could be accomplished with a rather densified network of metasurfaces that can be dynamically optimized for this kind of purposes. But definitely, when talking about metasurfaces and use them in a large extent within the network, it's critical to understand what are the deployment scenarios, how to deploy them, and in different scenarios, how can those metasurfaces be being optimized. For example, you see some results here. These are very relevant to deliverables of our project, and a recent paper written by all of the partners, where you see typically on the top left, you see the connectivity and reliability boosting by a single metasurface. There was a connection between a base station and users, but we want actually to increase the SNR, but we put a reflector in order to provide these extra degrees of freedom in terms of realizing efficient beamforming towards the user. This could be one use case, which is one scenario, which is quite general, and many use cases fall under this. Or it could be, if we go on the top right, in cases where there is a blocker, and instead of putting a conventional relay or another base station, realizing even, for example, a small cell, we put various metasurfaces that we try to optimize together with the transmission of the base station in order to serve users. But we can even envision more sophisticated applications, as you see on the bottom left, many RISs, and with each of them being actually owned by a dedicated set of transmitters. Base stations you see there could be the same operator, or even more visionary, different operators, where of course we need to treat this extra interference, and we need to ensure that a metasurface being deployed by one transmitter is not actually creating extra problems to another transmitter. If you're thinking about multi-operator cases, this is quite critical. You cannot envision that you have a typical wall where a building and currently becomes a smart building for one operator and could harm another operator. So there are certain regulation mechanisms that need to be devised for the technology to go further. We have been elaborating within the project a lot along these lines. And of course, on the bottom right, you see another application where we're talking about a RIS that could be shared among base stations, even if you think visionary, shared in time, in space, or even in frequency, which imposes certain, of course, fabrication challenges for those metasurfaces, depending on the case to realize it, as I mentioned before, by even different operators, and this could be quite relevant under the open run kind of architecture, where this openness, you share hardware infrastructure, this could be super relevant on a structure that is supposed to be within the environment and could be used by many of the transmitters, at the end of the day, different operators. But certainly, in order, especially, let's say, to go to realize this bottom application that you see in this slide, we have to be very careful of understanding the behavior of an RIS. Within the project, we came up with two critical, actually, metrics that are relevant, and you will see further details later on the relevant work packages about the RIS area of influence. So the specific area where an RIS will actually influence when it operates. This area could be actually optimized, right? We can even shape the size and the characteristics of this area, but certainly we need to know what are those characteristics of the area, and this is very relevant when we deploy it, what to expect, but especially we need to know also how this could influence a nearby transmitter, even if we consider in cases where being a different operator. Apart from the area of influence, there is also the bandwidth of influence. I mean, what is the specific bandwidth where the metasurface actually provides this smart operation, and where is what is the other portion of the bandwidth where it actually operates like a typical wall. This is again very critical if you consider multi-operator kind of applications. You will see later on in the technical discussion of the work packages more details on that. But let me go a little bit back to see where things more or less started, and I want actually to bring your attention here in one of the first work around the topic from actually a group in France. We had this great opportunity to have these partners within RIS-G of the realization of a 0.4 square meter RIS back in 2014, operating on Wi-Fi frequencies, which was actually used for two actually operations, which are very interesting. The one is to provide spatial and temporal focusing, meaning we can increase the SNR with this smart way within a specific dedicated to a specific spot in space, but we can also be used to provide this multipath enrichment. For those that have been working on MIMO, we know that in MIMO, we want channels that are full rank in order to provide this multiplexing game. But there are certain cases that this cannot happen. So the idea is why not using an RIS to create, to enrich the multipath within a channel in order to enable the application of a MIMO. And these things were actually being experimentally shown with 102 elements metasurface having actually 1 bit state, phase state of the meta elements. At that time, the power consumption was in terms of microwatts and the switching time a few seconds. Definitely many parts within the project and even outside the project are actually improving a lot those numbers, which is quite critical. But let me now go to the use cases and applications. There's the list is huge, but just to sketch a little bit, people have been using it a lot for communication to boost the spectral efficiency. So the objective has been spectral efficiency under the constraints of actually operating an RIS, energy efficiency, secrecy, electromagnetic field exposure. These are key KPIs within RIS-G, used for access, for backhaul, but also for localization, tracking, sensing, mapping lately. This is a very cool application, even 3D imaging, as well as simultaneous realization, I mean in groups, the integration, simultaneous sensing and communication, or even simultaneous localization and mapping. Applications for indoor, in offices, laboratories, factories, shopping malls, train station, which are the key field trials that we perform within RIS-G, even in vessels, tunnels. For outdoor, in mounting in buildings, their facades, even in rooftops to serve UAVs, or even being part in satellites, etc. But also for indoor to outdoor and vice versa communications by placing back-to-back RISs or even using transmitting of RISs or simultaneous reflecting and transmitting of RISs. You will see their schematic diagram later on, but also there are discussion about their shape, even not being planar, but being conformal metasurfaces to provide those applications. Other applications would be to jointly optimize the way we transmit our signals. We're talking about joint encoding of the reflections, embedding actually like index modulation as we do in multi-antenna system, embedding information within the reflection state of the metasurface, and we do a joint encoding with the way we transmit signals. This is quite interesting as an application, but even various others, this over-the-air computing that I mentioned before, applications in health, in energy harvesting, even for digital twins, which is a rather challenging application but could be very relevant to the technology in the sense that if it's easier let's say, densify a network with entities, right, that we can use for sensing, for highly accurate 3D sensing. This could be a way to realize those super demanding applications like digital twins. So this 3D dynamic representation of physical objects within the environment. And of course, localization, as I mentioned before, here you see a survey that we have performed within WP5 in this project of enabling localization in 3D with passive RISs. And you will see, if you notice, if you take a careful look at this figure, that you could provide localization compared with conventional ways by using smaller numbers of base stations. So we can replace transmitters, typical transmitters or typical receivers with passive metasurfaces, and again, having localization. We're talking about the efficiency of getting localization. Of course, it could be also used for SLAM. Here you see the SLAM case, where it's access point free in this specific case. So there's a user, there's a RIS, synchronization between the RIS and the user sends signals, it being reflected by the RIS and by scattering points, and you have the right amount of degrees of freedom if you also profit from wideband operation in order that the UI side to estimate your position with respect to the RIS reference system and the position of the nearby scattering points. Definitely, again, the notion of the area of influence of the RIS, and of course our own transmission plays a key role here. But definitely another cool application which has been lately studied is the utilization of the RISs for ISAC. And why is really critical their role there? Because it has been recently shown, we have actually elaborated with that, this is part of the project as well, where an RIS can provide this dual factor kind of gain. So it provides additional channel paths through to these extra reflections that it provides, which means more channel gains, which can be used either for sensing or communication, which at the end of the day translates, in this figure that you see here, as a means to expand the respective subspace, the space of the sensing and the subspace of communication. But also, if we optimize the RIS atomization, what we can do is we could rotate, those specific subspaces, meaning that we can actually correlate even more the subspaces that referring to the communications and those to sensing operation, which actually means that we get into a regime where ISAC plays a huge role. So long story short, with RISs, you can actually create more channel paths, but you can actually correlate even more the sensing and the communication oriented channels, which actually means that you can profit more by the integrated consideration of communication and sensing. And this is the critical role that RISs can provide into this specific topic. But of course, in order to do that, as I mentioned before, in order to optimize the RIS, we have discussed a little bit about the potential, You need to know certain things about the environment that they operate. So at the end of the day, what we optimize is the operation of the metasurface, is the reflection operation of this metasurface, which means it's like a beamforming kind of technique, So it's a channel dependent technique. I need to estimate the channel. This is one of the major difficulties to do it with an RIS, especially when we're passive, meaning that we don't have the capability to estimate at the RIS side. We need to do it at the communication ends, and this translates into augmented overhead in order to do that. But before going to channel estimation, we need, of course, to devise algorithms. We need to have models about the way that the RIS actually influences signal propagation. So here you see a typical way of actually modeling things where the configuration of each element, it's actually modeled by a phasor where we can dynamically change its states. In practice, it will have distinct discrete phases. And in principle, the output, the channel, the end-to-end channel, it will be a channel which is parameterized over the configuration of the RIS, which in general, it's non-linear. Although many works consider that this actually relation, the way that the RIS actually impacts the channel, imposes a linear form. This is the so-called, in blue that you see here, the cascaded channel model, which has actually monopolized in a way up to recently, the way people have been using in the end-to-end channel modeling of an RIS, or even multiple RISs. Here you see one in this model, in order to devise, I mean, objectives like rate, right, whatever SNR, and then perform optimization over the constraints. But lately there is a lot of discussion about the generic model, which is non-linear, and this is actually imposed by two factors: the proximity-induced mutual coupling due to the nearby element of the RIS, but there is also, it could be especially in multiple kind of applications of the technology, this reverberation-induced log rates coupling that needs to be accounted for. Within the project, there has been a huge work about trying also to model not only the way that this phi matrix that includes the tunable phases of the phase is being modeled, and there have been models which are from circuit theory, and even the end-to-end, these matrices. Here you see this H2, H1, H are typical random matrices, but could be matrices that have a form, they come up from physical electromagnetic based models, or others that are related to circuit theory kind of understanding, interpretation of the system. So there are a lot of things, fascinating things happening along these lines. I don't have the time to dig into that. Just to give you an expression here, to see this reflection modeling via transmission lines, where you see at the end of the day that this reflection coefficient, which is tunable by the RIS, actually can be expressed by a specific, let's say, circuitry, which can be characterized, can be incorporated in our formulas and do certain stuff. This is for a specific kind of modeling, and could be, it's not as generic as it could be. There are different ways to do that, modeling a realistic behavior on the RIS. You will see discussions under W3 later on. But when talking about RIS and this end-to-end modeling, people have also been working on optimizing those reflective beams, right? So it's a beamforming technique, as I told you before. So many times we need in advance to fabricate, to design dedicated code books, and dedicated code books that actually result from practically constrained RIS, right? When in cases we have very low bit resolution or even dedicated states, there is a mechanism within this project, within this paper that was conducted within WB5, or even going for code books, which will be very relevant for beam management, even if we're thinking about near-field kind of applications. Hierarchical. Why? Because one way to optimize the RIS is by performing channel estimation. As I told you, is quite critical before, because anytime you send pilots and you want to estimate the end-to-end channels, the receive signal depends on the configuration of the RIS. So what you usually do at the receive side, where you perform to estimation, you use many configurations in order to estimate something, to devise dedicated tools to do that. The other way to do it is, instead of going for explicit channel matrix estimation, you could go for parametric parameters of the channel, like angles, impinging angles, outgoing angles, etc. Or you could use code books. Hierarchical code books could be a smart way to do it, because you reduce the amount of time you're searching over the code book in order to optimize the RIS. But let me go now. Okay, this is, let's say, the almost passive, as I mentioned before, RIS, but there are many others that have been discussed, are being discussed out there, and also within the project. This transmissive RIS that you see here, where one of the partners, CLED, has done pioneering work on that, where you see at the end of the day, we're talking about a RIS where you illuminate it from one side and you get this transmissive behavior from the other side, and you can have very accurate beamforming. This is one way of thinking of a RIS, which again comprises of tunable state metamaterials. Or simultaneously transmitting and reflecting RISs. You could envision that indoor to outdoor or vice versa applications, you have a window, you put, it could be even a transparent RIS there, and it would be great if you could have reflections tunable and retransmission on the other side, refraction, tunable refractions that also serve users within a room, for example. This is another architecture that has been discussed. But also, as I mentioned before, due to the fact that you have this the path goes through the RIS, and you have these path loss, which can be large, and at the end of the day reduces the how far you can use a RIS and what you could achieve, and at the end of the day influences this area of influence of the RIS, right? People have been talking about providing amplification elements to the RIS. One way is to use amplifiers, dedicated amplifiers in each element, or even using architectures where you amplify whatever is being impinging on the output of the impinging signal of certain elements, and this output, which is a combined output of all let's say the output of the impinging signal of the elements, you amplify this, you feed it to another RIS, and then you get RIS reflection in a way using smaller numbers of amplifiers. Apart from this, within the project, we have worked a lot on this hybrid RIS architecture, where the idea is to fabricate an RIS with elements that they are capable of simultaneously transmitting and receiving. The idea there, this can be actually done. I don't have the time to go in details, but there you can use actually waveguide in order to direct a portion of the impinging signal on each element, and you can drive it to a circuitry that you can enable you to measure things. This could be a reception RF chain. And actually this reception RF chain does not necessarily need to scale with the number of elements that are hybrid elements here, right? You can have a single reception RF chain, and the combination of the waveguide is being connected to all the elements that are hybrid and drives their superposition within an RF chain, and you can use this measured signal to perform certain kind of estimation. But of course, in order to do that, the controller needs to be capable to perform baseband processing, and definitely there are trade-offs that one needs to decide there, how much hardware complexity, computational complexity you could afford to do certain stuff. But of course, there was a motivation behind that. The motivation behind the hybrid RIS is to enable the RIS to perform certain forms of estimation in order to lower the overhead, right, to perform this channel estimation, which at the end of the day, to lower the overhead, to optimize the RIS. And this can even enable this so-called self-configure RIS by using in a smart way the impinging signal, a portion of it, while simultaneously performing tunable reflection. This can actually lower down, right, the amount of time you need to optimize the arrays. Of course, there are, in the same spirit, there is this passive RISs where you embed sensors. Instead of having, as I said before, hybrid meta elements, now we're talking about a metasurface, and there are some elements that could be like sensors, or they could be like receiving antennas, which again, you drive in baseband, you estimate, and you can do certain things. This has been used, for example, these receiving RISs have been used also. Here you see you can have three, and you can perform localization of the user. By profiting, this is a narrowband application of these guys. You can have an angle estimation, angle of arrival estimation of the impinging signal in the far field should be, of course, in order to apply that. And then you can perform intersection of lines or a similar approach in order to get the location of the user. But those hybrid RIS that I mentioned before, they can enable this, as I mentioned, this self-configurability. And one way to use it is as you see here. For example, you want to estimate certain tunnels, and you could have the users, you could have the base station, both operating in the transmitting mode, sending orthogonal pilots. The RIS estimates the channels and actually performs, it's the RIS that performs the optimization for the overall system, for the overall operation. But of course, you could use it to even improve the channel estimation. If you don't let the RIS to do it, you can use the RIS to estimate the challenge between itself and the users, and then you could use with a dedicated controlling feedback channel. Of course, it requires extra overhead. You can fuse the end-to-end channel estimation and the channel estimation that you have at the RIS side in order to improve the overall estimation at the end of the day. Different architectures, I don't have the time to go into the details, reconfigurable intelligent computational surfaces where you could envision different layers implementing analog computing on even your morphic computing metamaterials to embed extra smartness to metasurfaces. People lately are also discussing about beyond diagonal RISs, meaning that you could envision embedding actually extra very cheap elements interconnecting different elements of the RIS in order to, at the end of the day, to dynamically or even in a fixed way change the mutual coupling, the interaction between those elements. Of course, this will requires extra hardware, but it provides more degrees of freedom that can be optimized, right, to improve the performance. Of course, theoretically, this has been shown compared with a typical diagonal RIS. But another very interesting application, which you will notice probably the similarity with the hybrid RIS, because they have the same idea behind that is you could envision using metasurfaces as a replacement of the RF front ends of typical transmitter and receivers, meaning at the end of the day, it's like a way of implementing hybrid analog and digital beamforming, and instead of having conventional antennas, you have a metasurface at the transmit antenna, a metasurface at the receiving antenna, and you can profit also for the propagation within each microstrip, which actually a microstrip is a collection, is the layer that has these printed meta elements there that determines their placement, their interactions, and can be used to provide the form of analog beamforming. This has been actually discussed within the paper, and it could be, it seems to be a very promising application for this holographic MIME, or way of realizing those extremely large antenna array systems by dynamic metasurface antennas. Going further, there even this stacked intelligent metasurfaces paradigm, where instead of having one metasurface, you could think of stacking one metasurface after the other, even placed on a box, and try to move certain form of the transmit receive beamforming within the structure in order to do things completely in the RF domain. But let me go to the challenges before I wrap up. So you have seen some architectures there. There are certain things still that we need to understand in order to unveil the potential of this technology. And one of the major things is to see which are the capacity, which is the capacity, right? The achievable rate limits that we can get with this technology. And this needs to be actually studied well. In this paper, within the project, what we have done is we have used tools from statistical physics in order to understand what could be the capacity in the large antenna regime, where in a network where you have one transmitter, one receiver, and multiple RISs. And what we have seen is that the optimization of a RIS plays a huge role when the channels are a low angular spread, while when we go to reach scattering and we have a metric which is the ergodic mutual information, there even on average change the configuration of the RIS or having as a dummy reflector doesn't really provide a difference by trying to optimize it, meaning estimate channels and do all the things. But the good news is when we're in the low angular spread regime, you could optimize the RIS with closed form expressions, and you can get this fascinating result, this gain, and this has certain implications in the way that we can optimize networks with RISs, and especially we consider that we provide a form of a hybrid RIS, which is a smarter RIS, to enable certain form of estimation. This could be done in a more efficient way. These are things that are being discussed later on, and apparently this work very soon. We have the version where we go into the MAC channel, the incorporation of multiple transmitters, and try to understand what are the gains in this network of multiple RISs. And of course, this is the vision of this environmental artificial intelligence, meaning having various RISs distributed around the area, being here you see a case being controlled by a single controller. It could be different controllers in a distributed way. We have been this is one of the discussions within the 60 DISAC, a new project which actually came up from many of us within this project consortium, where we're trying to understand how we could efficiently optimize a network with multiple RISs, and if we want to see if AI tools, machine learning tools could help us in order to do it in an efficient way, meaning that we want to deviate from having to estimate all those channels, which is impossible if we think in practice, and could be being done in a smarter way. The idea is that it can, and we have been elaborating within this paper on a deeper reinforcement learning, on a reinforcement learning formulation. We use deep approach to use it. Emilio, yes, 2 minutes, and I will close to do that. So this is quite promising to do this optimization. The placement is a huge problem with RISs. Where you put them, here you see an example, the position arrow bound of a specific application to provide positioning placement of RIS. If we change the position of the users, the shape will be different. So we still need to optimize for a given, let's say, map, geographical map, the way we place the RIS. RIS could be also coded in moving vehicles, and this could be used to enable their more efficient optimization. So we go up to, we get into regimes where we want to estimate the position of the RIS. These are cool applications. And of course, I mentioned many times around my talk today, the design of the control channel of the RISs. This is quite critical. I mean, to understand what is the overhead and what is the right way to optimize the beams. Do we do beam searching? Do we do channel estimation? And if we do channel estimation, how we do it? Do we need to incorporate a more sophisticated architecture to do it, to pay an extra load, an extra cost for the hardware to do it? But of course, another interesting thing before closing, what about using malicious RISs? D2E later on in WB6 will discuss about that. RIS could be used in a bad way. How can we confront these kind of very typical issues? But also, this consideration for holographic MIMO that I told you before, the synergetic utilization of metal surfaces with even other technologies like full duplex to enable ISAC. Various challenges to close. The characterization of all these RISs, even for the multifunctional and efficient information exchange protocols, modeling. We need a lot of modeling still for the mutual coupling, the interactions with scatterers, the fabrication of multifunctional RISs. It's an open topic. You see various designs, but still we miss the architecture and new applications, low latency beam tracking schemes, wave-based, this computing near-field algorithms, computationally autonomous and self-configuring RISs. So these are one of the very cool things. So we're trying to convince you here it's a good technology, strong technology, rather cool for do certain stuff, as we mentioned here, and Emilio, and you will see later on. It can be optimized even for ISAC. Personally, I believe it can be a strong enabler for the ISA, which is a paradigm being discussed will be discussed in release 19. Hybrid RIS could be a way to provide a lot of gains. Proof of concept we still need, going up to large frequencies where we see that to be the killing application of the metasurface. And this is the time for me to close the discussion. Emilio, thanks for your patience to go some minutes ahead. So thank you, guys.
Thanks a lot, George. Thanks a lot. So I will propose the question will be mainly on the chat, because now we have this timing which is quite strict, and actually during the panel.